non quelli da fuori. Quindi la puoi portare anche in strada. Infatti i trascentrali li fanno anche le chiavi diverse, li faccio
in streaming questa cosa, va bene?
Sì.
Va bene a te?
Certo.
Sì, l'ho mandata qua internamente.
Non dirò parolacce.
No, va bene, però dovresti firmare la liberatoria 1, 2 e 3.
Ah, questa è l'email, non devo firmare ora. Guarda che sotto c'è la carta carbone con la cambiale.
Forse l'email, se no un po' di assegno.
Così se vuoi un paio di giorni si possono organizzare, si vede sicuro, anche perché voglio capire esattamente come far funzionare e iniziare, anche perché necessariamente a capire vuol dire fermarci davanti a una. Ciao, sono Roberto Ragazzoni, io ti devo presentare, credo, Luciano vado probabilmente presentato un'altra roba bra. Sai questa virtù della. Io sono il bra, cat, faccio il bra là e il cat lo faccio qua. Quindi mi dai 2 minuti. Ok, volentieri. E mi ha detto, scusi, ma volevo presentarmi prima per evitare la scena di fingere, no, mi sono seguito qua.
Vai un attimo di là.
Ok. Dico saluti e torno, vedo che sta ancora arrivando un po' di gente.
Sì, va bene.
Ho chiesto a Corsini se c'era qualcuno del Dipartimento che voleva presentare. Però perché Flavio non c'è. Devi portare i saluti di Flavio.
Ah, ok.
No,
potevi portare il tuo saluto di Flavio, non mi ha detto niente. Flavio mi ha detto che non riesco a venire a quelle 2:30, ma ci sono ancora delle 5 per fare gli onori lui di là.
Benissimo, quindi hai 2 minuti per rilassarti. Qui c'è anche la loggia delle donne.
C'è la loggia, sì, là mettiamo
i meno capaci. Adesso l'architettura è questa, non ci puoi fare.
Sì, è l'aula più grande che abbiamo. Quella di oggi è.
Questi non possono scrivere. In realtà è soltanto questo qui.
Ti hanno detto del microfono?
No.
Ti serve? Forse sì.
Ah, sì,
No.
non so. Posso metterlo se c'è?
Però c'era vediamo la mattina. Ciao Giulia. Ah, siccome tu sai se c'è anche l'uso di un microfono? Quelle? Che brava. È che tu stai in piedi giustamente. Aspetta un attimo. Il numero per chiamare la mattina, come faccio?
io ero uno che leggevo gli articoli quando ero ragazzino, quindi...
L'unica cosa che desidero è che sei breve, no.
Sì, io sono...
Vai a chiamare un
Benissimo,
attimo,
basta che...
grazie. Un attimo che stiamo chiamando per il microfono.
Stati Uniti e Germania, adesso sei direttore di fisica teorica. Tu sei triestino, te?
Barese, cioè sono nato a Milano in realtà, però sono pugliese di origini e ho studiato a Trieste, mi sento mezzo triestino, ecco. Ho fatto 2 figli a Trieste.
E se prende questo in mano non funziona. Okay, it's a pleasure and an honor to have here Luciano Rezzolla to speak about the first image of a black hole, and this is a joint seminar with the Dipartimento of Astronomia, where we are guests here. So unfortunately, Flavio Senior was unable to reach us, but I give you the greetings also from his side. And as the director of the Astronomical Observatory of Padova, thanks again for you to be here. And also, just in case there will be at 5 p.m. a public meeting, a public presentation to the general public on the same subject. So here you will have the hard questions. I am supposed to give a brief curriculum of Luciano. The most tricky things I have to ask to him from exactly where he is born in Milan, but he feels from Bari, but he mostly lived and feels more from Trieste, so it's a real Italian, true Italian.
Exactly, yes.
Okay, and it is interesting that the first stage of his career has worked with Shapiro. That is someone that I remember also. I read the paper when I was much younger with so a great name. Okay, and now he's director of the Institute for Theoretical Physics in Frankfurt am Main. And I don't know if I have to speak a bit more in order to wait for the microphone to arrive. The microphone is arriving, so I have to say something more than, no, it is arriving. So thank you again, and thank you, Luciano, for being here with us. We are just having on the other building an industry meeting for the big science. So it's perfectly matched. It's very difficult to have a microphone working. These technological things.
Okay.
Okay, thank you.
Yep, it works. Okay, well, thank you very much for the presentation. Thank you all for being here. It's a great pleasure and an honor to be in this place. It's beautiful. I hope you appreciate how nice it is to come here every day and see such a beautiful and historical building. So, the title of my talk is about the first image of a black hole. You are scientists, you are doomed to be skeptical. I hope I will convince you that what we have actually taken an image of is a black hole, and that it helps understanding, a lot about what goes on in astrophysics. So, here is the plan of my talk. I'll give you some very soft introduction about M87 star, that is the object at the center of the M87 galaxy, which we think is a black hole. I will explain a little bit in terms of observation, how you actually do this in practice, you need a technique. I was not aware of this technique, so I hope this will not be too elementary for those of you who are experts in this technique, but at the same time, I hope that those of you who are not expert will appreciate a bit how this whole thing works. And I will explain more from a theoretical point of view, which is really what I have been working within the collaboration about, how you actually convince yourself that you're looking at a black hole. And then, as I said, because as scientists we always have to be nurturing the doubt, I will ask myself the question, are we sure we're seeing a black hole from Einstein theory? Or another question I could ask is, are we sure we're really actually seeing a black hole and not something else? And I'll try to give you at least partial answers to these questions. So nowadays, you're not a serious scientist if you don't have a fancy movie that shows what you've been doing. And I am a very serious scientist, so I do have a very fancy movie. This is a movie that ESO has done for us to explain what we've done. It's very romantic. You're looking at the Virgo cluster. There is a galaxy cluster. At the center of this galaxy cluster, there is a galaxy, M87, which was erroneously thought to be a comet because it had this filament coming out of it. Now we know it's not a comet, it's actually a galaxy, and that this is an ultra-relativistic jet of plasma moving at the speed of light. And if you zoom in, leaving the optical and going to the infrared and then into the radio, you find out that at the center of this jet, there is this object over here. We think this is the first image of a black hole, and I'll try to explain first how you obtain this and then why we think it's a black hole. So what was this? The technique we use is called VLBI, Very Long Baseline Interferometry. EHT has not invented this technique. It's simply used to the leading edge of the technology. And as in many things in astronomy, this technique is based on this very simple equation. The resolution, the angular resolution of your observation is the ratio between two quantities. One of them is the wavelength at which you are making the observation, and the other one is the size of the telescope, the dish at which you are collecting this information from. Okay, so you would like to, have light that is coming from the neighborhood of an accreting black hole, because you know that light will be produced. However, you also know that most of the light that is produced near that black hole will actually be absorbed, will not reach us. Especially the very high energy light will be absorbed on the way. So you want some wavelength that is sufficiently, for which matter between us and this object is sufficiently transparent. And you soon realize that this is radio wavelength. However, with radio wavelengths, there is a problem. So if you were to do an observation at centimeter type wavelength towards the galactic center, that's the kind of image you will obtain. A very diffuse halo of the size of a few tens of milliarc seconds. And really what you would like to have is something of the order of tens of microarc seconds. So you want to go at least 3 orders of magnitude down in resolution. And the reason why you have such a diffuse emission is for two reasons. One is that the amount of the light that is producing this emission is not only coming from the center, but also coming from its neighborhood. And the second thing is that at these wavelengths, there is a scattering that is produced by the electrons between us and this object. So what you want to do is to go to higher frequencies, which means smaller wavelength, and so going into regime of gigahertz or terahertz. And when you do this, something nice happens. First of all, the scattering is suppressed, and second, the actual size of the emitting region becomes smaller. So you can play this game, and already when you enter into the millimeter range, you start seeing something which is, a few tenths of the size of the horizon. And then if you go further in at 1.3 millimeters or 230 gigahertz, then you have enough resolution to sample something on the scale of the horizon. Now, when we started this was a bit of a guess, because in order to know exactly the resolution, you need to know the mass of the object. The mass of the object tells you the size of the object, and we don't know the mass of M87. We knew it by a factor 2. So we've actually been very lucky that M87 is more massive than the pessimistic expectation. And so we have enough resolution at the end of the day. Now, if we have fixed the numerator here, we still have to fix the denominator here. And so you want a radio telescope, something that can collect this light, these frequencies. Radio telescopes can be built to be rather large. You can have 500 meters radio telescopes, but this would still not be enough to get the micro-arc-second resolution that you wish. So what you want is something that is as big as the whole planet. You want a virtual telescope which has the size of the Earth and that can observe at these wavelengths. And this is what EHT is all about. So EHT doesn't possess telescope. That's why it's such a cheap experiment, because we didn't buy or build any of these telescopes. We just used them. And so the idea is that you have telescopes in Europe, South Pole, in Chile, Hawaii, US, and then you put them together. Put them together into this technique, which is interferometry. The idea is that you are recording not only you're looking at the same object, you're looking at the same object at exactly the same time. And when you do this, you are virtually getting the same wavefront. Clearly, in order to be able to do this, you need to have extreme precision in the way you record the time of arrival of the signal. And that is why, to do this technique, you need atomic clocks at each of these telescopes, so that together with the signal, which is essentially an electric field variation, you also measure the time of arrival. And so you measure all of these in many different telescopes, and you can put them together in a correlation and produce interferometry. So all of these telescopes have atomic clocks. Some of them didn't have atomic clocks, but then EHT and the funding stakeholders have equipped them so that they could make these detections. Now, in principle, you need just 2 telescopes to do this, but you actually benefit from having more. The reason why you need more is that 2 telescopes will see the source just for a very short amount of time. And really, you would like to have an integration time which is as long as possible. And you can do this because the planet rotates. Because the planet rotates, there's going to be always a certain number of telescopes which is looking at the source, and so can record data. And all of this can be then combined in the Fourier space and give you an image at the end of the day. And that's exactly what we've done. So in April 2017, we have sent a number of people across the globe to make this observation. You can see there were people in Mexico, in Chile, South Pole, Hawaii, Arizona, and Spain. All of these people were then making observations at exactly the same time and recording them. And here is a first piece of miracle that happened. If you think about it, it's a bit paradoxical. You're trying to get light from an object which is 55 million light years away. And it's sufficient that you have clouds 10 kilometers above your telescope, and you will not see this light because it will be absorbed by the water vapor just above your head. And this is, the miracle is that, as you can see from these photos, all of the stations had perfect weather. And that helped. The first time we tried, we had the best weather conditions. We've taken more observations later on in 2018 and 2019. We never had such a good weather. So we were lucky, definitely lucky, the first time we tried. Okay, then in April 10, 2019, we have announced our results, and this is April 11th, so the day after. As you can see, essentially all of the newspapers, the main newspapers, have produced this. I think somewhere is La Repubblica. But more than the newspapers, this was a fantastic source for social media. It has been estimated that 4.5 billion human beings have seen the photo in about a week. So this is a good fraction of the whole planet. The whole planet has by now seen this image and knows what is this image. And of course, everybody thinks it's a different thing, but I'll try to explain that we believe this is a black hole. So let's have a look at the source. The source is M87, this galaxy, and as I was telling you, there is this jet that comes out of it. If you look at in the radio at centimeter wavelength, you see that actually the source is very large, 240,000 light years. And with VLBI, you can zoom in into this object so that you can look at this object and see more in detail here and you can start seeing the details of the jet. This is several kiloparsec long. It may help to have an idea the amount of collimation of this jet. If you think this is water, this water, and as the water has a size of about a meter in diameter, this flow of water would be collimated between here and New York, just to give you an idea in normal scales. You can zoom in, you can find out more details, and further zoom in, you can study all the different knots. You can also learn that these knots move at almost at the speed of light. That's why it is an ultra-relativistic jet. And if you want to have an idea how the technological jump that we have done with EHT, this is a typical resolution pre-EHT, and this is the resolution we obtain with EHT. So it's this technological jump, rather than a new technology, that has allowed us to make these observations. I like this cartoon because it really gives you an idea that we're talking about astronomical objects. The sizes are huge, okay? So this is the solar system. It barely fits inside the shadow, and this is the location of Voyager 1, the furthest away satellite we launched. Okay, so how do you actually do the observations in practice? I already told you a little bit about VLBI, but let me go a bit more into the details. I've explained that you have different telescopes, that you can correlate their signal, and this is shown with these baselines of different colors. Now, any of these correlations gives you information in terms of visibility, which is the Fourier transform of the signal, in this space, which is a visibility space. And at any time, you just have a dot, a single piece of information. But then as the planet rotates, these you cover different, because the baseline and the orientation changes, you cover different portions of this space. And out of this information, you can build an image. More mathematically, you have a certain brightness amplitude, which is a function of the coordinates on the sky, x and y. And then you Fourier transform this, just like you would Fourier transform a time-varying signal, to obtain this complex function, which is a visibility, a complex visibility. And so out of this complex visibility, you obtain an image. Ideally, this space, if the space is fully covered by color, then you would have a perfectly sharp image. In practice, you cannot do this, but you can try and fill it up as much as possible. That's why it is so important that you integrate as long as possible, and that is why you need many telescopes. And so if you have longer tracks in this space, you have a sharper image. Okay? What I'm showing you here is a real simulation of what happens. So you can become larger and larger. The details become sharper because you're sampling smaller portions of this visibility space. Now, something you may be more familiar with is the Fourier transform between space and frequency. Okay, so imagine that you have power spectral density. This is the power spectral density of a signal, but this power spectral density is not continuous. You just have patches of power spectral density, and yet you would like to reconstruct a time-varying signal. You know that this is not possible unless you fill up the holes between these densities. And the same can be done here. You don't know exactly what is the information that is missing here, and so you have to put in some assumptions. And these assumptions are normally based on humanly decided assumptions, which are most natural and most obvious. Okay, if there is a certain continuity, you assume that, and so on. But it's an assumption. There are people who've done this type of work for decades, know exactly all of the artifacts and how to stay away from those. But nevertheless, DHT wanted to avoid this human bias step. And so what has happened is that once the data was cleaned up and calibrated, it was given to 4 different teams. And each team could analyze the data with whatever software they wished, whatever technique they wanted, whatever assumption they fancied, but being independent from one each other, being actually blind from the results of each other. And then after 2 weeks of work, they have obtained the first rough cuts of what the data was giving them. And these are the first rough cuts. And this is where our excitement really became, reached went through the roof, because, well, these images are different and yet they are similar. They're all showing that there is a ring of emission, that this ring is not uniform, and there is a clear signature. All of the images are showing something more bright at the bottom. And that's exactly what we were expecting, and I'll explain why we were expecting that. These are the 4 final images after we cleaned up more of the mistakes we were making in the beginning, and these are what are called the consensus images. What you can see is that these images are not the same, and I'll explain why this cannot be the same, because essentially the light producing these images is changing because the accreting matter on this object is changing continuously, but overall they don't change in shape. And that's also what you would expect, because M87 is a 6 billion solar mass object, cannot change on a time scale of a few days only. So these images not only match our expectation, also match what we were, all of our simulations say. So how do you do this in theory? We were given these images from our colleagues, observers, and they said, okay, we've done our job, this is what we think is the right image, now you tell us what this image is. And we had a couple of groups doing the theory in the collaboration, and one of the big groups was in Frankfurt, and was possible because of this ERC grant that we received, Heino Falken and Michael Kramer and myself. And in particular, the group in Frankfurt was working on the theory of this. It's called Black Hole CAM. And I think it's really, we should be proud as a European we have received this funding, because it's not only allowed us to play at an equal footing with the much more rich colleagues in Harvard and the MIT, but also has really triggered a competition effort that has poured money into the US and has allowed this to take off. Anyway, when you look at the theoretical work, there are 3 main steps that are needed. The first one is called GRMHD simulations in arbitrary space-time. So you want to perform general relativistic magneto-hydrodynamic simulations, and you want to be able to do them not only in general relativity, but in any space-time you can choose. This is telling you what happens to matter when it falls onto a black hole. It tells you about the variability, the typical properties, the level of symmetry, and so on. It's telling you the temperature distribution, the pressure distribution, and so on. So if you want, it's a bit like doing weather predictions. We need first to know where the clouds are going to be or when they're going to be formed, and then later on we need to ray trace them so that we can tell what they will look like when observed, whether it be luminous or not. And then at the end of the day, once you have done a lot of simulations and you built a lot of synthetic images, you have to compare with the observations, which are much fewer than the actual theoretical images. And we have built 3 different pipelines for doing these 3 different steps. The first one is called BAC, it's a GRMHD code. Then we have BOSS, which does the ray tracing and radiative transfer, and GINA that does the comparison. And the real heroes of all of this story is these people over here, who are students and postdocs who worked in Frankfurt. Some of them are no longer in Frankfurt. They moved to different faculty jobs later on. So because I am a theorist, I need to look at the equations, and the equations I need to solve are these ones. So I need to solve the conservation of energy and momentum. So I have a covariant derivative of the energy momentum tensor. I need to conserve rest mass or current. I need an equation of state that relates pressure with some other property of the fluid. And if I'm doing magneto-hydrodynamics, I also need to take into account electromagnetic fields. So we'll need a Maxwell equation in terms of the Faraday tensor. And the energy momentum tensor over here is really the composition of that of the fluid plus that of the electromagnetic fields plus or whatever you want to put in. So these are the GRMHD equations, and these are solved using 2D or 3D simulations and finite volume approaches. So this gives you, the temperature and density distribution. Then later on, you want to solve how light is emitted and absorbed, and you have to do this not on straight lines, but you have to do them on properly curved geodesics. So you need to solve a radiative transfer equation along the path followed by photons. And I'll explain why this is a bit tricky. Now, if you if you ask yourself, okay, you have a covariant derivative. This means that you need a background metric out of which you can compute this covariant derivative. And so which gravity model are you assuming? Well, first of all, the reason why I don't need to solve for the answer in the equation is that I can consider this space-time to be fixed. The amount of matter in the disk and in the light is so small compared to the black hole that is really moving on a fixed background. And so test particle motion is perfectly suitable, which is a big advantage because all I need is just a metric tensor. A metric tensor g mu nu, which is a function of coordinates. And of course, general relativity gives me already this metric function in the case of rotating or non-rotating black holes. But I don't want to marry general relativity. I want to be as agnostic as possible. In particular, there are hundreds of different theories of gravity which are not general relativity, and you would like to see whether or not they produce the same predictions. So what we have come up with is a way to represent any metric theory, in particular any metric, black hole metric, in terms of a generalized description. So instead of having a metric tensor of this type, you have a metric tensor which is also encoded into some coefficients, which are the results of an expansion. So we take general relativity as our reference, but then we can build out of this reference any metric, black hole metric or non-black hole metric that you wish. The reason why this is possible and works well is because we played two important tricks. One of them is a conformal mapping, and the other one is the use of a rapidly converging Padova expansion. But these are mathematical details. What is important is that whatever black hole you are in love with, you give it to me and I can express it in this form, and then I can simulate what a black hole in this theory would look like. And then I can measure some coefficients. In principle, this is what I would like to do. Take an image, measure the coefficients, and learn from the coefficients which gravity theory is the right one. And I'll say whether this is realistic or not later on. Now, a point I should remark, and I would like to impress, is that tracing photons near a black hole is not easy. You all know what this is, right? It's a laser pointer. And the reason why I can use a laser pointer, that is I press a button and I know there is going to be something glowing on that screen, is because light moves on a straight line. And this is because the curvature in this room is essentially zero. But if I were near a strong gravitational field, say a black hole, I will not be able to do that. I could point there and maybe the light could go behind my back. So you have to be very careful when treating light in a curved background. And to explain this better, let's use this cartoon. You have a black hole over here. You have a thin disk which is emitting light. You want to take a picture of this at a given inclination. And there are going to be a number of photons which will make up your image. There's first going to be the direct image. That is, the photons coming from the disk straight on almost straight lines and hitting you. These are going to be the portion of the disk right in front of it. And in a flat space-time, that's all you would see. You wouldn't see behind the black hole. But in a curved space-time, that can happen. So you can see that light emitted that would not otherwise reach you can be bent suitably so that it reaches you. And so all of a sudden, you see also the part behind the black hole. And even more bizarre, you can actually see the light that comes from below. And so that's the typical image you should expect of a thin, luminous disk. You probably have seen this image before if you watched Interstellar. Now you appreciate why it looks like that. Okay? It's really the combination of direct images and indirect images that you see over. Now, there is an important object here, which is this dark patch. This is called the shadow. And it's important that you distinguish the shadow from the event horizon. And to clarify this, suppose that you have an event horizon and a black hole and you have some source of light behind it, so that you have a swarm of photons being produced. There are going to be the photons that go right into the event horizon straight away. And this will be clearly captured and absorbed. But there are also photons that are not going right into the event horizon, but near it. In particular, within a sphere, which is called a photon sphere. And And also these photons will eventually be captured. Okay, so they will go around, and then after a while they will be captured. So the event horizon has a size of 2m for a Schwarzschild black hole. The circular orbit, that is the edge of this, capture, not capture, is 3m. And then if you ask yourself, what is the projected section at infinity? Mathematically, this is the impact factor at a circular orbit. This is square root of 27m. So this is roughly 5. Okay, so these are the numbers which are important. The radius of the shadow is 5m. The size of the horizon is 2m. You have almost a factor 3 difference. Something also you can appreciate from this cartoon is that the shadow should not be dark. I said if you send light here, some of this light will be captured, something will be transmitted. But if I emit light over here in front of the black hole, then there is no problem for this photon to actually reach me. So the shadow is not a completely dark region. It's a darker region in the image. And that is why we don't see pitch dark. We see rather a high density contrast in intensity, a factor 10. Okay, now the shape of the shadow depends on the spin of the black hole. If it is non-rotating, spherical symmetry means that you must have a spherical shadow. If you have a rotating black hole, then this is a bit more complicated, and the shape of the shadow, as seen being edge on in this case, so the spin goes up in this way, would be like so. So it's asymmetric. There is a region which is flatter than the other one, and this is because there is frame dragging that is distorting light motion in this direction. Of course, if you were to look at it from the top or from the bottom, you would still see a perfectly circular shape. But if you see it edge on, you would see this shape. So ideally, knowing the shape, if you can measure the circularity of the shape, you can tell something about the spin of the black hole. Another point I would like to make is this interstellar type. I should really say Luminé, because Luminé was the first one to show this, but everybody is familiar with interstellar, a few with Luminé. The shape depends on the inclination angle. And in particular, if you are looking at it exactly face on, you would see a perfectly round ring with no asymmetry whatsoever. On the other hand, if you start changing the inclination, then the image will differ. And of course, in principle, we don't know what is the inclination, and this is something we have to factor in when we do our analysis. Okay, I hope I've explained a little bit how light propagates near a black hole, and you have a clear idea of what happens to light coming from a thin disk. Well, whatever you have understood, forget it, because that's not quite what we see. What we see is actually coming from an optically thin but geometrically thick torus. And so the kind of image that we should expect is something like this. I'm rotating this so that you can see how the intensity changes left or right side, how the shadow becomes either a perfect circle when it's perfectly phase on, or becomes two different shadows if you're seeing the objects edge on. But something that is important, and is always true, that in general, unless you're looking at this pathological exactly face on case, there's always going to be a bright side and a dark side. And that's because the dark side is where light is, or matter is moving away from us, and the other way around, the one coming towards us is going to be Doppler boosted, and so the intensity will be increased. Okay. By the way, if you have any question, just interrupt me any time. I'm happy to be interrupted. As I explained, in this theoretical analysis, one important step is understanding what happens to matter. And so what you do is simulation. This is a prototypical simulation, one of the many we've done. You start with a torus which is in equilibrium, but then it's subject to an instability, the magnetorotational instability. This drives accretion. What I'm showing you is the density, while over here is the magnetization, the ratio between magnetic energy and rest mass. So essentially in this region you have a lot of magnetic energy and very little mass. And what you can appreciate, so this looks like computer graphics, it's not, it's really a 3D GRMHD simulation. What you will appreciate is that the motion is turbulent, highly turbulent, and also the accretion rate is highly turbulent. So there's going to be times where there is a lot of matter getting in, other times where there is less. There are regions where there is a lot of density increase and other where there is less. And this is what we expect to be true also in M87. I'm now orienting the simulation in the direction where we think we're looking at the jet, and I will switch from MHD to radiative images. So now is what that simulation would, how the light will be produced. And as you can see, this, you don't see most of it, you just see the very inner edge. And it looks like it's almost a uniform density, uniform emissivity, but it's not. The image is really complicated and it's lens, but you don't see that just because of the very lucky inclination angle. And if you now deconvolve with the sensitivity of typical instruments, that's a kind of image. And the variability here is of the order of 24 hours. So an M87 looks flickering in this manner over a time scale of several days. But what is important, is the shape doesn't change. This is what we observed, and I will now explain the final step, that is how you compare the observed image with the actual simulation. This is just to give you an idea of the actual size and of the object. So there is few images, but you want to compare these images with all the possible realization of an accretion flow onto a black hole. The space of parameter is determined by the dynamics of the plasma, which depends in itself on the black hole spin. So counter-rotating or co-rotating, where counter and co are relative to the angular momentum in the torus, and the accretion type. Essentially, there are two main ways in which a magnetized accretion torus works. One is called a sane accretion, the other one is a mad accretion. These are acronyms, stands for standard accretion or magnetically arrested disk. And you can play with, you can produce either one by just playing with different magnetic field configurations. Then the light dynamics. So that tells you about the plasma. Now you want to know about the light. The light depends on, and so the shadow size, that depends on the black hole mass, which we don't know. Depends on the microphysics of the emission, which we also don't know. What we know is that it almost certainly synchrotron emission. But as you remember, synchrotron emission requires energy distribution of the electrons, which we don't really know. And then, of course, there is a position with respect to two angles of the inclination with respect to the observer, which again are unknown and need to be varied. What we know from other sources, not from imaging, is astronomical information about the mass. We know there are two estimates from star dynamics or gas dynamics, which are in tension with a factor 2. The inclination angle, which we don't know, is either 17 degrees or 163 degrees. And the position angle, the projection onto the sky, which we know is 288, at least at large scale. We also know the X-ray luminosity of M87 and the jet power. And all of these are information we don't use, at least not when in our paper, we don't use this information. But we use them later on to remove some of the uncertainties. Now, in my view, the most severe uncertainty is about the electron temperature, the way light is produced. We know it's synchrotron, but you need to know the energy distribution, and if you say that the energy distribution is thermal, you need to know the temperature of the electrons. We don't know the temperature of the electrons because the only temperature we know is that of the ions, the heavy part of the flow. So you need a way to link the ion temperature to the electron temperature. And you want to be able to decide phenomenologically whether the light comes from the disk or comes from the jet or comes from a composition of the two. And this cooked up expression does exactly this. It uses the beta parameter, so the gas over magnetic pressure, so that you can play around whether you have light coming mostly from the disk or mostly from the jet. And then you have an additional parameter which allows you to increase or decrease the emissivity in different places. This is a purely phenomenological expression. Is almost certainly incorrect because it doesn't give us the full spectral energy distribution, but it's a simple way to describe, to go from temperature to emissivity and therefore to imaging. And we have played around with this value in this range over here. So the first thing to do, as I explained, is do simulations. We've done about 50 high-resolution, three-dimensional, long-term simulations. You need long-term because the system has to reach stationarity, and so you have to throw away most of the actual simulated data so that you can concentrate on the few days of good stationary flow. And about 50% of these simulations were done in Frankfurt. Then by playing with those scenarios, that is, playing with the electron temperature, and you can build a number of different, what we call scenarios. And just to give you an idea, this is just a small portion of the library of scenarios that we produced. So each of these simulations differs because maybe the spin of the black hole is different. See, for instance, here the spin is positive, so you see the flow is co-rotating. Here it's counter-rotating. Some emission is very broad, some is very, very concentrated, and this is all the different prescriptions that you obtain by changing those parameters. Just to have an overall picture of the two different accretion modes, the same models are like this. You see, you can have contributions. So these are different spins. These are different values of R high, that parameter, while these are MAD models. MAD models tend to be more concentrated near the light ring. The light ring is this nice ring that you see over here, which is really the edge where photons can be captured. And this is just a position of the black hole axis. Now, you may ask yourself, and that's the question we asked ourselves. So we have an image, we produce an image. Can we tell where the light comes from? And I want to impress on you that this is really a hard question. So please don't ask me this question. Just to give an example why this is so hard, I'm considering a co-rotating black hole, but rapidly rotating, 0.94. So the ISCO of the disk is right here. This is the photon orbit. In a curved black hole, this is no longer a single surface, unless you are at the equator, at the poles. It's really a region. And you can think that this is the inclination angle with respect to which we observe. This is R high equal 10. This is R high 160. So this is the edges of our range. This is a MAD simulation. This is a sane simulation. You can see that just by playing with R high, I can have most of the emission coming from the disk or from the jet. When I say the jet, I really mean the sheath. So the region, almost the most external region of the jet, because there is where the most energetic particles are. So in the case of a co-rotating black hole, I certainly cannot tell you exactly because it depends on the parameters. Things become even more complicated if you have a counter-rotating black hole. See, the ISCO now has moved further out, and here you will never have any contribution from the disk. You just have the contribution from the jet. In the case of sane simulations, in the case of MAD simulation, the situation is a bit more complicated. So you can think of doing the following exercise, because we have produced everything, so we can tell you where does the light come from, at least in synthetic images. We can take these synthetic images, which are just picked up from this sample, and then we can split into the different components. What is coming from the disk, what is coming from the jet that is towards us, what is coming from the jet that is away from us. Even that jet is actually contributing. And this is shown here in this mid-plane column, near side jet, far side. And what you can appreciate is that essentially it all depends. In the case of this model, which is MAD R high 10, most of the light, 90+%, comes from the disk. Very little comes from the jet. If you look at a sane simulation, you see that most of the light actually comes from the receding jet. So a lot of the light in that case is actually converted back into the image. So that is why if you ask me where does the light come from the image we observed, I would have very high difficulty telling you where, because it can come from many different locations. Okay, so we build these many scenarios. From each of these scenarios, you have days and days of possible images, and you can build a library of images. So we built 60,000 images, And now is the final step. Go and compare 60,000 images with 4 observations that we have. And for this, we had to, again, go back and start from scratch, learn how to do genetic algorithms, searches, and Markov chain, Monte Carlo simulations. If you want and interested in this part, let me just give you an example. So this is a synthetic image. This is the deconvolved image, as you would see in the image space. In the visibility space, you would, in the visibility space would be, you would have the data, which is the blue point, and the model, which is the green points. And of course, there's going to be a difference as the image changes. You can calculate the chi-square for any of this image, and then you can find a chi-square distribution, and then find out which of the images best matches. I think it's easier to think in terms of images rather than visibilities, although mathematically it's much easier to work in visibilities rather than in images. So imagine that you are at a stadium. There are 60,000 people in the stadium, and you have an image of a person that is potentially in the stadium. You don't know. So what you do is you just scan all of the photos of all the images in the stadium, and you build a distribution of matches. So these are all the potentially all the best matches. Then you sort them in terms of best match, and this is the 10 best matching images. So this is a typical artificial intelligence example of algorithm, and you immediately realize there is a lot of artificial and very little intelligence, because obviously you would never think that this is the right image, right? But the software clearly picked up a very close overlap, probably because of the eyes. Another thing that you learn is that none of these images is the right one. The person was not in the stadium. And it is also true. We have 60,000 images, but our are the result of theory and assumptions and simplifications. Reality is far more complex than what we can simulate. So we don't expect to have a perfect match. However, sometimes we do get a very good match. This is quite impressive. This is observations, which is theoretical model. If I flipped, I would know myself which one is the observation, which one is the theory. So when we saw things like this, we thought, wow, we know exactly what's going on. We can tell everything about M87 star. Unfortunately, this happened too often. These are 3 different images. So these are the synthetic images. These are the deconvolved images. All of these 3 images give you exactly the same chi-squared match with the observation. So they are equally indistinguishable from the observations. And yet, this is a counter-rotating black hole, this is a Schwarzschild black hole, a non-rotating black hole, and this is a co-rotating black hole with a mad type of accretion. So obviously, we are not able to distinguish the spin. Okay? So this is, at the same time, good, because we are confident, no matter what black hole it is going to give us something that looks like that. It's bad because, at least now, we cannot tell the spin on the basis of the image only. But there are other tools we can use. So, as a result, in our published data, we don't give any information on the spin of the black hole. These are what we think we measured, and the most important quantity maybe is, the size of the diameter of the ring, its contrast, more than 10, the deviation away from circularity, the mass of M87, 6.5, 10 to the 9 solar masses. Okay, so hopefully this settles the issue between gas dynamics and stellar dynamics. And but this is not enough. It would be nice to have more information and say something about the spin. And this is where you can put in the additional information. Okay, so knowing what is the inclination angle, which we haven't measured, but other experiments have, we can come up with 4 different scenarios, and this is clearly these 2 are not what we observe. We observe something like this. So it has to be one of these 2, and we actually believe is this one at the bottom in particular. So there is a small inclination angle. The spin of the black hole is pointing away, and so it's more like something like this. The spin is moving in this direction. The rotation in the, not so much in the disk, but in the funnel is in this direction. So it's the same, very near to the emission region, which is producing this, is clockwise, while at large scale becomes counterclockwise. This is nothing bizarre. It's just frame dragging. Very close to the black hole, you would see something that is frame dragged along the direction of the spin of the black hole. Okay, so this is what are our predictions. We also don't believe it's a Schwarzschild black hole. Although the images are degenerate, Schwarzschild black holes do not produce enough power in the jet. You can produce a jet, but this is less than what is observed. So we feel that there isn't, this has to be a Kerr black hole. Well, it has to be a spinning black hole. Now, what type of black hole is this? As I said, we all believe it's a black hole, but we've done a lot of simulation with Kerr and Schwarzschild, but are we really sure that this is not another black hole in another theory? We love general relativity. It is the best tested theory of gravity, but in gravitational physics there are many alternatives, and one of them is a dilaton black hole, or a better, in Maxwell Einstein dilaton axion black hole. Okay, we call it dilaton black hole for short. And so it's fair and right to ask ourselves, how would a dilaton black hole look like if we were to do exactly the same analysis? And here comes the first complication. You want to compare apples with apples, and you can't because they are two different black holes, but at least you want to compare an apple and an orange, which have comparable properties. Okay, so what you can do is you can choose a Kerr black hole with a given spin, 0.6, and then play around with the parameter of the theory. In particular, there is a parameter called the dilaton parameter, such that the dilaton black hole either has the same size in the horizon, the same size in the photon orbit, or the same size in the ISCO, in the innermost stable circular orbit. Okay? In this way, you are comparing things which are different, but at least have one property which is identical. We have compared all of them, and the conclusions don't change. So let me just show you an animation of a simulation where you have a Kerr black hole and you have a dilaton black hole. The size of the black hole is different because what we matched here is the ISCO. And if you look at this simulation after a while, you see, well, the ISCO is at exactly the same place. The dynamics is pretty much the same. You can look more in detail in the plasma dynamics, but that doesn't really matter because you will never be able to go and measure the plasma properties. What you can measure is an image. And so this is the image coming from Kerr, and this is coming from a dilaton black hole. And this is for Sagittarius A star. This paper was built with having Sagittarius A star in the head. And Sagittarius A star also suffers from scattering, so really what we expect to see is more something like this. And so you compare these two images by eye, and you say, oh, wow, they are very similar. You can ask some algorithm that measures the difference, and you realize that also the algorithm would not be able to distinguish them. So overall, at present, given the present resolution, we can now distinguish different black holes, at least not a Kerr and a dilaton black hole. And that is why the title of my talk is the first image of a black hole, not of a Kerr black hole. However, I can still ask myself another question could it be something else? Could it be not a black hole, but something which is almost like a black hole, looks like a black hole, walks like a black hole, but is not a black hole? There are these objects, these are called black hole mimickers, because they are built to look very much like a black hole. And one typical example is a boson star. Okay? So a boson star is an object that doesn't have an horizon, but is nevertheless extremely compact. And boson stars are very appealing at a galactic scale because you can think that they are what make up the dark matter. So it's not a completely crazy idea. And in the past, people have asked themselves this question: can you actually distinguish a black hole from a boson star? And the answer that people have concluded by looking at static configuration is that it's not possible. But we have done the first GRMHD simulations. Interesting. Either there is an earthquake or... No, but it's the projector that is vibrating. Okay, we'll check if there was an earthquake at 3:30. Okay, so let me show you what happens in an accreting boson star. You can see there is a torus which is feeding in, and then there is a brighter region, and then there is a black region. Now, we call this the mini torus, and if you were to calculate where the mini torus would be in an equivalent black hole with the same mass, would be inside the event horizon. The reason why there is a dark region is not because there is a black hole, it's because there is no matter there. And there is no matter there because matter cannot go right to the center, because there is angular momentum conservation and there is a centrifugal barrier. So as matter falls onto the black hole, just like in a Newtonian potential, there's going to be a centrifugal barrier which will prevent going to zero. You can probably appreciate this better from these simulations over here. These are x, z, and x, y sections. This is a Schwarzschild black hole. This is a boson star. You can see that the horizon is larger than the actual mini torus. So what happens is that matter in a boson star just goes in. There is no horizon. But then at one point we'll find a centrifugal barrier will accumulate there in the form of a torus. So where does the matter then go? Well, if it cannot go in, it has to go out, right? And that's what you actually can see here. Matter in a boson star is ejected in terms of a relativistic wind in the polar axis. So there is no jet, magnetic jet, but there is a jet of matter. You can look at this in terms of plasma properties, and you can see that in the case of a black hole, the accretion rate is always one sign, while in the case of a boson star, it actually changes sign, and most of the matter is actually ejected. Again, comparing images, you see this is a Kerr black hole, this is a boson star. You can use again the scattering, and you can compare these two images and ask yourself, can you distinguish them? So what is clear is that the shadow, the dark patch here, well, it's not the shadow. The shadow is true just in a black hole. A boson star would not have a shadow because there is no horizon, but there is a dark region, and this dark region is much smaller. If you want to make it larger, you can, but you need to increase the mass of this object. And on the basis of what we observed, we cannot increase the mass without violating the constraints. And so that is why we conclude that for the observations we made, this cannot be explained in terms of a boson star. So what you have to bear in mind is it is possible to distinguish them, and in particular for M87, we don't think we've seen a boson star. Okay, I want to conclude on time, so maybe there is some time for some questions. Black Hole Camp, this European project, has provided important input to all of what EHT has done. In particular, we've been exploring Kerr black holes, and I explained that we try to look at from all possible angles, and there was a lot of work done in a very short time because people in the past were not even asking themselves questions like where does the light come from or what does a black hole look like. We also have started looking at alternatives to Kerr black holes. We don't believe these are plausible. All of the other theories of gravity are artificial in a way or another. They require fields that we don't see anywhere else. They don't have a really astrophysical genesis. To produce, for instance, a dilaton black hole, it's not clear how you produce a dilaton black hole when you have a normal star. But nevertheless, science has to be agnostic. And when considering other black holes, we've seen that it's hard to distinguish them. We need higher resolution. But we can distinguish other objects, those that are possibly horizonless. Overall, EHT has provided, in my view, the first evidence that supermassive black holes exist. This may be something you consider not very relevant. I think it's very important because that was an assumption. Now we have evidence that this is true. Every galaxy, or most of the galaxies at their center, have a black hole. And we have learned a lot about strong gravity. Also, we've shown with EHT that this type of observation is possible. The idea that you can image a black hole, if you had asked someone just maybe a couple of years ago, they would have said it's impossible. A, because you cannot possibly image the event horizon, which is still true, but you can still convince yourself there is a black hole without getting information from the event horizon. And technologically, this is possible. So I think there is a new era of astrophysics that has started, and there is much more that is going to come in the near future. Thank you. Yes, questions?
I saw that concerning the data point of view, all this work has been done probably not more than several days of the data. Okay. What happens in terms of perspective? I mean, will you have more detail if you, in few days? I understood that things changes in a matter of days because
yeah, that's a time scale.
You cannot integrate it longer because. So, what are the perspective of the research? I mean, are you going to observe again M87? Are you going to observe other?
So, what we observed in 2017 was both M87 and Sagittarius A star, and Sagittarius A star was our favorite source. But then we immediately realized it's much harder to model, and so we switched to something which is more stable like M87. We have the data on Sagittarius A star, and we hope to publish them early next year. It's harder, much harder, but it's still doable. The prospects are, well, campaigning. You know, the difference between this and LIGO is that we know where they are, and we can go over and over and over with increased resolution. If you put more telescopes, you get better resolution. If you increase the frequency, you get better resolution. If you have an optimistic view, maybe you're going to get an order 5 increase in resolution. That's still not enough if you want to ask these very difficult questions. Is this a curve or is this a different black hole? So the real future for this type of observation is space. You can do VLBI from space, sending satellites, not very large satellites, 4-meter antennas, and then you would have, in a few months only, you can fill up all this visibility space essentially without having holes, and that will give you the type of resolution that you want in order to answer these questions.
How do you reduce the resolution given the maximum distance between two?
Yes.
Telescopes?
Right. And so
Now it's nearly,
so by having
the distance now is the.
Yeah, but you have to place in space. So if you
Ah,
satellite at
okay, so let me first say if you are on Earth and you place different telescope at different distances, then you are able to sample not only the finest scales, but also the larger scale, okay? And if you are in space and have satellites, so the configuration we have in mind, and might be easier if I just show it to you, is something of this type. You have 3 satellites on nearby circular orbits. No, well, so this would be in space, right? So you can also play having one station and one satellite, but this is easier to understand. So these move at different frequencies. You can have baselines with change in size, and so they cover different regions of this visibility space. And within 6 months, you would have something of this type. Let's see if I can, yeah. So after 6 months, you would have this type of resolution, and this is, you know, enough to answer some questions. Now, you would think people are excited about this. We have put in a suggestion to ESA. Hasn't seemed to be very well received so far. We've not even been invited to discuss it. But there you go.
How expensive would that be?
Not very expensive. You know, these are 4-meter telescopes. These are nearby, 15,000 kilometers. So, you're not talking about LISA. It's rather, cheap in space budgets. But, yeah, I think it's, we need to convince people that this is doable. I think people are not yet convinced.
Roberto and then Nico.
apparently there is a convenience way. There's a comment.
Oh, okay. Right now we have to explain.
This solution is roughly, it's on optical wavelength on a 10 kilometer time space. So it means it's hard to make interferometer technique. But if I do interferometer at this baseline, I am of course observing it visible. I will see very similar things, different things. The contrast is different. The amount of photons.
I think you would not be able to see much because all the light would be absorbed. That's a real problem. That's why you go to VLBI.
So even reaching that resolution in the visible way.
Yeah, because all the optical or high energy would be absorbed by whatever is here and near it. I mean, there is a lot of matter. There is plasma around it, as you've seen from this large scale radio, and that would absorb most of it. Yes. Yeah, actually, but it's larger than the stellar dynamics. And we think that stellar dynamics is simply over-optimistic, okay?
And the question is that when you calculate the error, you marginalize all the
Yeah,
parameters?
yeah.
So it is not the error that take into account all the changes of all.
So it is marginalized in this respect. You're taking into account all the systematic and uncertainties in the actual data, and then in the actual modeling of the data. Yeah.
The much closer stellar sized black hole, can we observe with this technique?
Unfortunately not. They are too small. Well, first of all, we know that there are stellar-sized black holes, few tens of solar masses, and those are few kilometers, tens of kilometers. The sun has a 1.5, one solar mass black hole has a 1.5 kilometer radius. So no matter how close they are, I mean, I don't know if they are in the solar system, maybe they can be seen, but hopefully not. Yes.
What about galaxies? You have the black holes.
Yeah, so there are 4 potential candidates. 2 are the ones we've looked at. Then there are, I think one is called M84 and another one is a number I can't remember. So there are at least 2 other sources. These are not as good as these ones, but if you can get an increase in resolution of a factor 3, then they become, then you start having sub-horizon resolution. And after those, it's much harder. It's much harder. So there isn't a whole zoo of sources that you can look at. But yeah, I think, well, yeah.
First of all, congratulations.
Thank you.
It's very, very amazing result and amazing project. And also because, I didn't understand what is behind all this tremendous also computational effort that we work on numerical modeling.
Yeah.
So I can really appreciate it. Still, so my question, you invited us to be skeptical.
Right. Not critical, just skeptical.
And I saw, in your discovery paper, there is one point in the visibility which seems to really stay off with respect to the 50 to the 46 microsecond disk.
Yeah.
And this is very important. So, it is always a problem reconstructing images, as you can imagine, in the system which you were so careful, from the visibility and the coverage of the UV plane.
Right.
It's still relatively incomplete.
Very incomplete, yeah.
The question is, what is the reason for that? And aren't you worried that until you get really better sampling of this plane, you may actually really be off in terms of management and the modeling of this plane, lead you to something which is not perhaps this?
Yeah, so I think the sticking point is a LMT, so it's a telescope in Mexico, where we think the estimated error bar is overly optimistic. So that point sticks out, and looks like it is, really sticking out because the error bars associated with it are very small. Now, we can't, possibly go against what our colleagues in the collaboration say is the error bar associated with it, and so we had to take it as correct. But we believe it is overly optimistic. And in that case, it would not stick out so much, and it would be compatible with the others. That is a telescope which has given us a lot of problems, has systematic variability within few hours, which are difficult to model. People think they know how to model, but it's a complicated instrument. Also, it's complicated also to manage it. In fact, right now LMT is shut down because of security reasons. There is a drug cartel that is threatening the personnel going to the telescope, and the Mexican government is not able to guarantee the safety of the employees. Yeah.
We want to thank again.
Okay, thank you.
Molto bello,
Grazie, grazie.
Adesso ti portiamo la